a crowd like this here. This is maybe the biggest crowd we've had, other than our gala, in the museum since the pandemic. So wonderful to all of you for being here. Thank you so much for coming. My name's Cindy Lawrence. I'm the executive director here. I'm also one of the founders. We just passed our 10-year anniversary. If this is your first time being here, oh, yeah, great. If this is your first time being here, welcome especially to you, and I certainly hope it won't be your last. If you want to know what other kinds of things we do, well, we've got all kinds of programs going on. Tomorrow, we have our Meet a Mathematician program that's online. You can meet Emile Davy Lawrence, who is a mathematician, and we'll talk to you about her life and her experience. Then the next day, we have Mobius Madness, which is a program where you learn to do some really fun things with a piece of paper. That's for late elementary and early middle school students. On Friday, we have two programs. We have our Folding Fridays program, which runs every week, and that's online. And we also have a discovery program here in the museum, The Secrets of Telling Secrets, which is a fun one. This Saturday, online, we have what we're calling our Mini Masters. Some of you may know we do an adult math competition, which turns math into a spectator sport. That happens February 28th, live here in the museum. But if you are not from the area or you can't make it here, you can participate online in an hour and a half on Saturday this weekend. And the top winner will get an expense-paid ticket to the museum if you're from out of town. That includes travel and accommodations. So that's on Saturday. Sunday, we have Who's Number One? That's the mathematics of ranking. Monday, for any of you who are educators, I'm very excited that we're having a professional development session. And that's a wonderful program to show you great ways to connect with kids around math in the classroom. For tonight, I'm very delighted that this is one in a long series we've had for many years now, partnering with Molly Dillon from NYU, the Lab for the Developing Mind. These are always fascinating programs about the intersection between how the mind works and mathematics. And I'd love for you to join me in giving a very warm welcome to Dr. Moira Dillon.
As Cindy said, my name is Moira Dillon, and I'm an assistant professor of psychology at NYU. I'm also the director of the Lab for the Developing Mind at NYU. My lab's been partnering with MoMath for about 5 years now to conduct fun studies here in the museum, maybe some of you have participated, looking at how mathematical concepts develop in the mind. We're also collaborating on new programming at the intersection of psychology and mathematics, and that brings us to tonight's talk series, Minds on Math. Through at least spring 2024, Minds on Math, co-sponsored by my lab and the museum and supported by the National Science Foundation, will feature accomplished scholars in developmental psychology, cognitive science, mathematics, and education who conduct research on how our minds and brains learn and appreciate math and related fields. This evening, I'm very happy to introduce Dr. Alison Gopnik as our Minds on Math speaker. Professor of psychology and an affiliate professor of philosophy at the University of California, Berkeley, Alison is also the author of 4 books, including most recently, The Gardener and the Carpenter, What the New Science of Child Development Tells Us About the Relationship Between Parents and Children. And she's a columnist for the Wall Street Journal's Mind and Matter column. Alison's work addresses the development of foundational human cognitive abilities, including causal reasoning, language, theory of mind, perception, and consciousness. Alison suggests that just like scientists, children can learn causal structure from the patterns of data that they observe. And she shows that children have much more powerful causal learning mechanisms than was previously supposed. She's also formalized her theories by exploring how probabilistic models and Bayesian inference can be applied to children's learning. Alison's received prestigious accolades for her work, too numerous to list here, but I note in particular that she is a member of the American Academy of Arts and Sciences and a fellow of the Cognitive Sciences Society. She's received the James McKean Cattell Lifetime Achievement Award for Applied Research from the Association of Psychological Science, and she's a recipient of the Carl Sagan Prize for Science Popularization. I note, too, that Alison has received a mentorship award from the American Psychological Association and is known in the cognitive science community, as you may have seen on several Twitter Twitter threads last week, as a champion for her students and her mentees, in particular providing guidance and support for those who decide to juggle academic life and parenting. In her written work, Alison expounds on the value of caregiving, from parents, grandparents, aunts, and uncles, to babysitters and preschool teachers, all of those people who help raise our human children. In fact, she proposes that human caregiving can even serve as a model to create better, more moral, and more intelligent AI. As an academic, parent, juggling parenthood and academia myself, I'm thankful for scholars like Alison, whose brilliance in thought and communication makes both science and society richer and more inclusive. This is why I'm particularly pleased to have Alison here tonight sharing her work. Please join me in welcoming Alison.
Well, thank you all so much for coming out on this sleety night, which I know you guys in New York are more used to than we are in California. This is my first venture out into the world post-pandemic, and I can't imagine a better place and a better group of people to be, doing it with. What I'm going to do today is talk about a whole lot of different work that I'll go through fairly quickly. But it really starts out with this idea that I and others have been arguing for many years, that we could think about little children, including babies, as being very much like scientists. Many of the things that they do are a lot like scientists. And in fact, I've argued that it's not so much even that children are little scientists, but scientists are big children. So scientists are people who continue to have the kind of curiosity that we see in children. And my first book, in fact, was called The Scientist in the Crib. Now, the question is, what is it that scientists do? And in particular, how can we describe the kinds of computations that are going on in science that let us learn as much about the world as we do? And obviously, various kinds of mathematics play a quite crucial role in that in formal science. But is something like that going on in the informal science that babies and young children are doing? So what is it that scientists do? Well, they do a lot of things, but here's three really important things that they do. They look at statistics. So they look at patterns of probability and conditional probability in the data around them, wherever that may be. So they're looking at what happens when something else happens. And importantly, they aren't just picking up those patterns. They're using them to actually make causal inferences. So they're using those patterns to try and decide what makes what happen out in the world. And picking up that causal inference, figuring out the causal structure of the world, making theories of the world, that's essential to science as anything could be. But not only are they doing that, but they're actually actively going out into the world, doing experiments to try to get more data so that they can make more causal inferences. So when they have an idea, a hypothesis about how the world works, they aren't just satisfied to have that hypothesis. They actually go out in the world, make things happen, and then figure out from what they happen, from the results, what further kinds of causal inferences they can make, what more they can learn about the world. And all three of these abilities are connected to certain kinds of mathematical structures. They all depend on the idea that you can use things like probability and data patterns to make other kinds of inferences. And what I'm going to do is talk about the fact that even very young children, toddlers, are doing things that are very much like this, and they're using some of the same kinds of computations that scientists use to try to solve these problems. All right, now that may initially sound crazy because anybody who's ever taken or taught a statistics course will tell you that grown-up humans in general are not good at doing any of these things. And my colleague, ex-colleague Danny Kahneman won the Nobel Prize for showing all the ways that people are bad at doing these kinds of things. But part of the reason I think why, this is what I think of as the if babies are so smart, why are grown-ups so stupid question, and I'll talk a little more about some of that later on. But certainly one reason is about how we ask about these things. So fortunately, in a way, we would never ask a 2-year-old whether they understood the relationship between conditional probabilities and causal structure, because the 2-year-old would have no idea what you were talking about. So how could we show that these very young babies can do can perform these kinds of computations? Well, we do it with very, very simple devices, basically toys. And this is one of the central things that we've used in our research. This is the Blicket detector. And the Blicket detector is a little box, and it lights up and plays music when you put some things on it, but not other things. And what we can do is actually show the children in real life, here's what the data pattern is using this very simple device. And even this simple device turns out to have a lot of different causal possibilities, as you'll see, and different ways that we can demonstrate data about how the machine works. And then what we do is we just ask them which one of these is a Blicket and which one isn't. Or even more simply, we just say to them, make the machine go. And then we watch to see what happens. So we give children data, we give them a chance to make a causal inference, and then we give them a chance to use that causal inference to go out in the world and make something happen. And just from doing those simple things, it turns out that we can figure out what kinds of computations the children are capable of. So let me start with a very simple study, but still, this is a study that we did with Andy Meltzoff and Anna Weissmeyer. And we did the study with children who were just 24 months old. So 24-month-olds are, just barely walking and talking. They're very little still. And here's what we did. We showed them that Blicket detector that I just showed you. And the way it worked, I'm embarrassed to say that the way that we actually set this up was we had our Blicket detector attached to a treat and train, which is something that you use to train puppy dogs, evidently. What it is a machine that dispenses things you can set it up so it will dispense things when you give it a signal. But instead of dispensing doggy treats, it dispensed marbles. And what the children had to figure out was if you put one block on the detector, then you'd get marbles. And if you put the other block on the detector, you put a block on the detector and then you could see whether the marbles would come out or not. Okay. And the way that this experiment went was that, as you could see in the previous slide, there's a red block and a blue block that the experimenter has. The experimenter puts the red block on the machine, and 4 out of 6 times when she puts it on, the machine activates. She puts the blue block on, and it only activates 2 out of 6 times. So you can see the probability of the machine activating given the block is different in the 2 cases. And then what we can do is just say to the baby, make it go.
Okay, Grandma.
Okay.
Okay. So she chooses the red block. And in fact, consistently, the children would choose the right one. They'd choose the one that had a higher probability of activating the machine, so the red one versus the blue one. Even though those are both probabilistic relationships, neither of the blocks is necessarily always making the machine go, but one is more likely to make it go than the other. Well, you might think, but were they really using probability? Maybe they were just looking at how often the machine activated. So in the second experiment, now we had the same setup, but now the children see that the red block makes it go 4 out of 6 times, and the blue block also makes it go 4 times, but it doesn't make it go 8 times. So it's 4 out of 6 versus 4 out of 12. So it's the same actual number, but now the percentages are different, and therefore the probability of being activated given the block is different. And the question was, would the children be able to do it that way? And it turns out that they did. So again, this is 24-month-olds. These are very little kids. So there's the probabilities. And again, the children consistently were choosing the block that had the higher probability of activating the machine. And of course, we counterbalance the red and blue and the sides and so forth. Okay, so that suggests that even little toddlers are capable of using patterns of data and probabilities to make causal inferences. But of course, that is an inference about which block in particular made the Blicket detector go or not. There's more abstract kinds of causal inferences that you could make. Maybe you could make an inference not about a particular block or a particular object, but about the relationship between 2 objects. And in particular, you could have a pretty abstract logical relationship that featured in a causal inference. And one of the classic examples of this is, could you learn relationships like same and different? So instead of learning that the red block makes it go and the blue block doesn't, could you learn that if two blocks are the same, they'll make it go, but if they're different, they won't, or vice versa. If they're different, they'll make it go, but not if they're the same. And a long tradition in comparative psychology, work with non-human animals, suggested that chimps, for example, have a great deal of difficulty trying to solve that kind of a task. So you show them that two things that are the same will always, lead to a treat. They can't generalize that to new examples, only after many, many, many trials. So we wanted to see what would happen with human toddlers. This is work with my student Karen Walker, who's now at UCSD. And here's what Karen did. You see two blocks go on the Blicket detector, and the Blicket detector plays music. And then you see two different ones, and it doesn't play music. You see two that are the same, and it plays music, two different who don't. And in the other condition, the different condition is exactly the same, except now it's when the different ones are on that it plays music, and when the same ones are on, it doesn't. Is that clear to everybody? Okay. And then what we did was just give the kids two trays, and now the two trays have different blocks, different shapes, different colors, but now there's two that are the same and two that are different. And we say to the kids, can you make the machine go? Pick one of these trays, see which one will make the machine go. And we did this with kids as young as 18 to 24 months, so again, very little kids. And the question is, which tray would the children choose to try and make the machine go? And what we discovered was that even with these very young children, in contrast to the chimps, for example, and even with just a few examples, the children were very good at doing this. And interestingly, they were just as good at doing it in the different case than the same case. So 80% of the time, really, really good for toddlers. They were choosing the right tray, even though, remember, the objects look totally different. They don't have the same color. They don't have the same shape. What's the same is this abstract sameness. So it's this abstract relationship of sameness, this abstract logical relationship that the children seem to be learning and using to make a causal inference. So that's for same and different. Then we wanted to try something even harder. So now, instead of just thinking about same and different, we decided that we wanted to see if they would learn what people in Bayesian inference call an over-hypothesis. What's an over-hypothesis? An over-hypothesis is a hypothesis about what kinds of hypotheses you're going to have. So for example, you might think, I don't know how the system works, but I'm sure that it's deterministic. I'm sure that the cause will always lead to the effect. Or you might think, I don't know how the system works, but I'm pretty sure that it's stochastic. I don't think that the cause will always lead to the effect. I'm not sure exactly which blocks are going to make it go, but I'm pretty sure that they have that kind of a structure. And as we'll see, you can do this in logical terms too. So you could say, all right, I think that this is a disjunctive relationship. Namely, I put the block on the detector, and either it goes on or it doesn't go on, right? And if a block is a Blicket, it will make it go, and if it isn't, it won't. That seems probably pretty obvious to everyone. But you could have other kinds of relationships. So maybe you put a block on the machine, and it's an inhibitor, and it keeps the machine from going. Or maybe you have to have two blocks together to make the machine go. So there's a lot of different kinds of general logical principles you could have about how this machine works, even before you know exactly the details about which blocks and objects are going to make it go or not. Is that pretty clear to everybody? To get it clearer, why don't you act as participants in this experiment. And I want to emphasize, because I'm quite proud of this, we did the experiment originally in 2014, but since then we've done it with a much wider range. We've replicated with a much wider range of ages, and we recently did it with low-income kids in sort of favelas in Peru and kids in Head Start programs in Oakland. And the kids in Peru and the kids in Oakland turn out to be just as good at doing this as the American kids are, which is sort of fascinating, and I can talk about later on. All right, here's a task that will give you a sense of this. So here's a Blicket detector, and here's all these objects. And your job, as I say, figure out how the machine works. So you see this pattern. D goes on the machine 3 times. E goes and nothing happens, E goes on and nothing happens, D and F together go on and the machine activates, and that happens twice. I think I've kind of had a spoiler alert here, but we'll see what happens. Okay, so how many people think D is obligate? Okay. How many people think E is obligate? And how many people think F is obligate? Okay, great. As I would have thought, a New York audience is as smart as undergraduates at California, but possibly not as smart as 4-year-olds. Because what if you also saw this sequence of events first? So now you see that A, B, and C go on the detector and nothing happens. A and B and C go on and nothing happens. But when you put A and C on together, that makes the detector go. All right? Now that tells you something about how, the logical structure of this detector, how this detector works. Well, this detector is a conjunctive detector. It demands that you have two causes rather than one, and it's the combination of the two causes that make the machine go. So just A by itself, C by itself, B by itself don't work, but if you put A and C on together, then it makes it go. Now, if you'd seen that, and now you go back, and now you're going back to that original sequence that I showed you, now what do you think? Well, if this is one of those detectors that works on that conjunctive principle, now the answer might be D and F are both obligates, right? Because if this is a machine where you have to put two on together to make it go, then it's D and F together that are making it go. Okay? Is that clear to everybody? So what we did was do exactly the experiment that we just did with you. We either gave people information that suggested the obvious thing, that it was disjunctive, that each individual obligate had the power to make it go or not, or we gave them evidence that suggested that it was this conjunctive, it had this conjunctive over hypothesis, logical structure, and then we gave them this test case, and we asked them to make judgments about the obligates, and we also asked them to make the machine go the way we usually do. We said, all right, now put some blocks on and make it go. And I'll show you, it was slightly more complicated than that because of Goddamn Reviewer 2. But here's what it actually looks like.
Very important, again, for us to figure out which of these are obligates. So let's call this one triangle, okay? What should we call this one?
Square.
Square. And what should we call this one?
Ball.
Ball. Sounds good. Okay, so let's see what happens when we put triangle on the machine. Are you ready? Let's see. Look at that. The machine did not turn on. Let's see what happens when we put triangle on the machine again, okay? Look, the machine did not turn on. Now let's see what happens when we put triangle on the machine one more time, okay? Let's see. Look, the machine did not turn on. Now let's see what happens when we put square on the machine, okay? Look at that. The machine did not turn on. Okay, now let's see what happens when we put triangle and ball on the machine together. Look at that. The machine turned on. Now let's see what happens when we put triangle, square, and ball all on the machine together. Are you ready? Let's see. Look at that. The machine turned on. Okay. Now let's see what happens when we put triangle and ball on the machine together. You ready? Let's see. Look, the machine turned on. So Scarlett, do you think that triangle is obligate or not obligate? Obligate. And do you think that square is obligate or not obligate?
No.
No. And do you think that ball is obligate or not obligate?
Yeah.
Yeah. Okay, so Scarlett, which of these should we use to make my machine turn on? Those two?
Okay, so I like this partly because, so this is a 4-year-old. If you're like me, even having done this a million times, you can't quite track what was that. It was like ball, and then it was the three of them. But that 4-year-old, as you can see, is paying a lot of attention. And in fact, she's getting it right. This was in the conjunctive condition, and she figures out that it takes this particular combination to make the machine go. So what we did was we did this in this PNAS paper with kids of different ages. And in the very first study that we did, first we looked at 4-year-olds. And what you can see is that the 4-year-olds are very good at inferring this abstract structure. Sorry, I should explain this. So this is how many times do you say that D is obligate? Think back to that first study that we did. And this is, do you choose one object or multiple objects to put on the machine to make it go? So if you figured out this unusual conjunctive structure, you should say 2 things are obligates. You should say that D is obligate, and you should put combinations on the machine. Does everybody got that? Okay. All right. So when we did the experiment first, what we found was the 4-year-olds were very good at doing the right thing given the evidence that they had. So if they had evidence that said that it was an or relationship, a disjunctive relationship, then they said D was not obligate. But if they had evidence that said that it was a conjunctive relationship, they said that D was obligate. They were much more likely to do that. And the same thing for actually intervening, for actually making the machine go. They were much more likely to use the 2 objects together in the conjunctive case than in the disjunctive case or in a baseline case. But here's the interesting thing. Here's the adults. These are Berkeley undergraduates. And what you can see is there's a little bit of a difference, but the adults aren't nearly as good at this task as the 4-year-olds are. So the adults have such a strong bias, what Bayesians call a prior, towards this disjunctive possibility, just like you did when you first saw that first sequence of blocks. They assume so much that it's going to be either a block is obligate or not, that even when you give them the evidence, they just go with what they think to begin with. They just go with their original biased idea, and they don't change their minds given the data, given the evidence. And that's true whether you look at they're saying it's obligate or not, or whether you look at what they do to make the machine go. Now, what we did in this study in PNAS was we were curious about what about in between the, and as I say, we've replicated this now in several different groups, including kids in Head Start programs and kids in Peru, in low-income families in Peru. So all those kids are smarter than all the adults. Okay, then we wondered, what is it that's causing this difference? Is it something about what your brain is like when you're an adult or a child, or could it also be just how much information you have about the world? So most of the time you're going to see these kind of disjunctive individual examples, and maybe you just get so many examples like that, again, in a sort of Bayesian way, that raises your prior, and you just assume that's the way the world works. And the more evidence you get, the harder it is to overturn that assumption. Or is it something about the flexibility of being a 4-year-old? Is there something about having a 4-year-old brain that is different from the adult brain? So what we did was we looked at 6-year-olds, 9-year-olds, adolescents, and adults. And what we discovered was the 6-year-olds are less flexible than the 4-year-olds, but they're still more flexible than the adults. And there isn't much change between 6 and adolescence. So even though that's 5 more years of experience, the 6-year-olds and the 10-year-olds are about the same. But as soon as you hit adolescence, you see this big change. You see this big decrease in flexibility. And in fact, the adolescents aren't different from the adults. So it's as if something happens in your brain when you hit puberty that's really changing the way that you're solving this kind of problem. Okay. Now, let me give you another example. Most of the time when you give kids and adults tasks, the adults are going to be better than the children. But that was an example where the children were actually more flexible, especially better at learning something unusual or unlikely than the adults were. So here's another experiment that we did. But in that experiment, we were giving the kids all the data. How about if you actually let the children get some of the data themselves? And in that experiment, it was just, did the machine go, did you make the machine go or not? You might think, well, look, if there was something riding on this, if you were going to get a reward for getting it right, maybe that would change the way that you would try to solve the problem. So maybe if you gave the adults some, money for getting it right, they would be better at being more flexible. So this is an experiment that we did with Emily Lequin, who is actually right here as a postdoc at NYU. And here's what we did. We had a Blicket detector, but now there's something riding on this Blicket detector. So the way that this game works is that you have 4 different blocks, and successively, one at a time, you put the blocks on the detector, and then you see if the detector lights up with a smile or doesn't. And you learn that ZAFs make the machine go, and we tell you ZAFs are going to make the machine go. And if you put it on the machine and it's a ZAF, you'll get a sticker. But if it's not a ZAF and you put it on the machine, then you're going to lose 2 stickers. When I give this talk in Silicon Valley, which I do because of our relationship to AI, I say, all right, make this like 1 billion stickers and 2 billion that you get and 2 billion stickers that you lose. All right, so now you've seen that the one with the white stripes is a ZAF and the one with the white dots isn't. And now you get another chance to test out the machine. This time, what you get is one with black stripes on it. Well, are you going to put it on the machine or not? Okay, you put it on the machine, and what you find out is the one with black stripes is a ZAF. It makes it go. Now, here's the crucial question. Now, and you get a sticker. Now, you've got one with black spots. And the question is, should you put it on the machine or not? Any votes? What do you think? No, right? Okay, once again, New Yorkers are as smart as Californian grown-ups, but maybe not as smart as kids. Because so you've got a good hypothesis, right? It's stripes make it go and spots don't. But it turns out that actually, if you put if you put it on, it is going to be a ZAF too, and you'll get more stickers. And the reason is that what makes something a ZAF or not is not this obvious one-dimensional rule, spots versus stripes. It's this more complicated and unusual two-dimensional rule. So things that are, let's say, everything is a ZAF except the white spots. So if it's either got a black pattern on it or it has stripes, it's a ZAF, and otherwise it's not. It's hard even to articulate it. But anyway, it's a very consistent rule. And what we found, so that's the way the rule actually works, and that's the way the rewards actually work. And we based this, by the way, on something that Todd Garekis, who's also here at NYU, had done. Okay, so you get 4 sets of these blocks, and you get to approach or avoid. And what Todd discovered was that if you do this with grown-ups, what happens is that they get stuck in what's called a learning trap. Because what happens is they get, just like you did, they get the idea about the hypothesis, and then they won't test it anymore because they're afraid that they're going to lose things, right? So they're not willing to take the risk of finding out that their hypothesis is wrong. And the result is, if you never test out to see whether your hypothesis is wrong, you're never going to find out that it's wrong, right? All you're going to do is just generate more data that fits with what you already know, which makes you feel more confident about what you already know, and you're never going to actually find out that you were wrong. So what we did was we did this with, and by the way, this is interesting, this learning trap idea is interesting not only because you're doing an abstract experiment in the lab, but it's also interesting because it's connected to a lot of clinical disorders, for instance. So if you think about something like anxiety disorders, the way that anxiety disorders seem to work is exactly like this. So you get on the plane, you have this terrible experience, there's all sorts of turbulence, you're sick, and then you just refuse to get on the plane again. And you never learn that actually, okay, most of the time when you're on the plane, it's okay, it's only occasionally that this happens. And in fact, that's part of the reason why the therapy for things like anxiety disorders or phobias is what's called exposure therapy, where you actually get to see that you aren't always going to have this negative outcome. Because once you start avoiding the negative outcome, avoiding the cause because you think it's going to have a negative effect, you're never going to learn that your anxiety isn't really founded in the world. So these aren't just theoretical, this actually has consequences, the fact that we fall into these learning traps. So what we did was we did exactly the experiment I just showed you, but now we did it with kids of people of different ages. And when we did it with adults, we got just the same results that Garekis got. So the adults tend to avoid the negative ones, But they also avoid the positive ones. So in other words, they also avoid some of the ones, they leave reward on the table. They avoid some of the ones that could be zoused because they're afraid that it'll turn out that they're wrong. And the 7-year-olds do this less, and the 4-year-olds do it much less, indeed. And if you just think through to your 4-year-old or to a 4-year-old that you know, the 4-year-olds just want to find out what's going to happen, right? They know that they're going to lose stickers, and they're kind of disappointed and crushed when you take the stickers away. But they just want to see what will happen, and they get a chance, you get a chance to see what will happen if you do this. That just overwhelms anything else about the stickers. All right, so that shows that the children were not falling into this learning trap, but here's the really interesting question. At the end, we asked them, how does this machine work? Does it work with this simple one-dimensional rule, spots or stripes, or does it work with this more complicated two-dimensional rule? So could you actually learn the way the thing actually worked as a result of the data that you'd seen? And what we discovered was that the children not only got more data and got the right data, but they also learned better than the adults. So most of the time, the adults were going with the one-dimensional rule, the simple rule that was inaccurate, that was wrong, and the children were much more likely to learn the more complicated rule. So just like in the example I gave you before about the conjunctive and disjunctive one, when the rule was sort of unusual, wasn't obvious, the children were better at learning it than the adults. And part of the reason for that was that the children just wanted to get the data. They seemed to be really driven to explore in contrast to the adults. Okay, so that's somewhat more exploratory, but it's still, it's still just, we're just giving them the choice of you can put it on or not. And if you watch babies, this is my adorable grandson Phalo, who's 11 months old.
Make it smaller.
They just spend all their time basically exploring. That's one of the things that they do spontaneously. And they'll just do it they'll do it basically for anything. I'll let this run a little as I introduce the next one because there's a nice insight at the end. So we wanted to try and see, would this be true if you just let the children just do whatever they wanted, just let them explore. What kinds of things could they find out just from going out into the world and exploring? But of course, the problem with that kind of thing is that it's hard to keep track of what the children are doing. So what we did was, instead of using a real live blicket detector, a real live machine, instead we gave the kids a kind of video game. And there was another reason for doing that, which I'll get to in a minute, which is that we've gotten very interested in comparing the kinds of computations that the children are performing, the way the children are thinking, and the way that artificial intelligence systems are thinking and solving problems. And if we give them, the kids, a video game to interact with, then we can literally give an AI system exactly the same game and then see what the AI system does, see if the AI system can figure it out. So by using these video games instead of the real thing, we can both track what the children are doing more carefully, and we can compare it more easily to a computational system. He's almost there. So do you see his solution? So he takes a good bite out of it, and then, of course, once he's taken the bite out of it, it's small enough to actually get into the bottle. Brilliant child. Okay. So what we did was we set up this video game. This is work with, again, my great graduate student Eliza Kosoy and a bunch of people at the Berkeley AI Research Group. And rather interestingly, when we started doing this work now more than 20 years ago, we used the machines, the real blicket detectors, because we tried doing things with screens, but the kids just weren't interested in pictures on screens. And in 2023, it turns out the kids are very happy to interact with something that's on a screen. It's one of those things that kind of was fortuitously came out of COVID when we couldn't test kids in real life, and we thought, I don't know, maybe they'll be able to figure this out if it's an interactive touch screen. And it turns out not only could they figure it out, but they really loved doing it, which will, again, not be a surprise to anyone who knows 4-year-olds. So this is the virtual blicket detector. And it's exactly like the Blicket detector that I showed you before, except that it's virtual. And here's an example of a child in a mask, because it's COVID time, playing with a virtual detector. And you can see that we have a little mouse, and the kids can put different things on the detector and then just see what happens. Sometimes the detector lights up, and sometimes it doesn't. So what we did was we just gave the kids this game to solve. And the way this game works is that half the time the machine has a conjunctive structure. So this is just the same as the one that I showed you before. Half the time the machine, you have to have two on at once to make it go. And for half the kids, it's the other way. For half the kids, it's just one or the other. So it's like those two different ideas about how the machine works that I showed you before. But this time, the kids are just discovering this by themselves. We're not giving them any data. They're just going out, and we just say to them, figure out how the machine works. Is that clear to everybody? I can go into more details about the method later. And what we discovered was that, first of all, the children did the right experiments. So they actually went out, and just in this spontaneous manipulation of the objects, about half of them did everything that they needed to decide whether it was conjunctive or disjunctive. They got exactly the right data. And even the ones who didn't get all of the data got appropriate data, got the right kind of data. And then when we actually asked them how many to make the machine go, do you put on one or do you put on two? And we asked them which one is a Blicket and which one isn't a Blicket. They got that right too. So just spontaneously, without us giving them any data at all, just spontaneously sitting there and playing with the machine, the children got just the data that they needed to figure out how the machine worked, and they drew the right conclusions about how the machine worked. So they learned how the machine worked, even when it worked in this unusual, strange, conjunctive way that adults seem to have a hard time learning. And as I mentioned, we've been doing a bunch of collaborations with Berkeley AI researchers. Molly's involved in this big project. And the very basic idea, this goes back to Alan Turing's original paper that you may have heard of, the imitation game paper, where he spends the whole first part of the paper describing the Turing test, which is how you could tell whether an AI was intelligent or not by trying to have a conversation with it. And then about halfway through the paper, he suddenly shifts gears and says, but Turing was pretty smart. Turing saying, you might be able to get a machine like ChatGPT that could pass this test, but that wouldn't be the real test. That's not the real test for intelligence. And everybody sort of forgot about the second half of the paper. The real test for intelligence would be, could the system learn from data the way that a child does? So could it actually learn how to solve these problems or have a conversation the same way that a child can learn? And that's been the real motivation for a lot of work that we've been doing in my lab over the last while. And let me just say, I won't go into all the details, we gave the absolute state-of-the-art reinforcement learning AI systems and the large language models like GPT exactly the same problem that I just showed you that the kids were solving. We told the GPT systems everything that the kids said. So we said, you have two Blickets, and the Blicket goes on the machine, and the machine lights up, and then you put three on, and the machine doesn't light up, and so on and so forth. And basically, they bombed. So the reinforcement learning mechanisms, they can solve the task, I have to say, and it only takes them 150,000 trials to do it. And the large language models don't get it right at all. Now, who knows, by tomorrow, there may be a better large language model that will, but at least for now, and that's consistent with what other people have found as well. These systems are quite good at having a conversation with you. They're not good at doing something new, like figuring out how a brand new system works. And I think that's actually quite a profound thing about how the AIs work, but I can talk about that later. Okay, so one question you might ask is, why would this be? Why would you get these effects of the children actually being smarter than the grown-ups in some cases? And that's part of a broader question, which is, why do we have children at all, right? Not the immediate answer, which probably people here have mostly figured out, but why, from a biological perspective, do we have children? Why do we have this very long period of childhood when children depend on us to take care of them, aren't bringing home any food are sort of useless and are, arguably worse than useless because we have to put so much work into just keeping them alive, giving them rice crackers. And this is a particularly important question because we have a much longer childhood than any other species. And in fact, if you think about, I like to think about an Alpha Centauran biologist coming to Earth in the Pleistocene and trying to figure out which of these little creatures that are scampering on the veldt are going to turn out to be the ones who take over, at least for a little while, take over the planet. She would not have seen very many differences in how good these creatures are at figuring out the physical world, or even how good they are at figuring out other creatures' minds. But if she was a good biologist, as surely she would have been, she would have said, there's something really strange about the way that this group develops. And in fact, in evolutionary biology, there's this really interesting concept called life history. And life history is the way that a species develops over time. Things like how long it lives, how long a childhood it has, how many babies it has, how much investment it puts into taking care of those babies. And it turns out that that life history predicts a lot about what the adult organism is going to be like. And that life history is often the thing that is selected by evolution. So if that Alpha Centauran biologist had looked at these proto-humans, she would have said, they have an incredibly strange life history because their babies are, so a human, a chimp child, for example, like the child in this picture, the baby chimp in this picture, is producing as much food as they're consuming by the time they're 7 years old. And even in forager cultures, human children aren't doing that until they're at least 15. And my son is 35, and you can see that for humans, it can be a really, really long time before they're producing as much as they're consuming. So why would that be? This seems sort of evolutionarily paradoxical. Well, that same biologist would have known that there's actually a relationship, a really striking and quite general relationship between how long a period of childhood a creature has, and to be anthropomorphic about it, how smart it is, how large a brain it has, how sophisticated it is, how good it is at learning. And the great examples of this are not just, if you look among different primates, you can see this, but you can see it also among birds. So if you compare our friend the domestic chicken, which is a bird that matures very quickly, is not terribly smart, or rather is very, very good at doing a couple of things, but not very good at learning anything new. You compare that with something like this New Caledonian crow. Crows and corvids are incredibly intelligent. They can use tools. They're as smart as chimpanzees, in many respects, smarter in some. And those crows aren't mature until they're about 2 years old. And this turns out not just to be true for primates and birds, it's even true for insects. There's even an argument that something like it is true for plants. So it's a very, very general, feature. And of course, we humans are way out on the end of the distribution on all of these dimensions. So we have a much longer childhood, much larger brain, much more flexible, better at learning about new environments. And what I've suggested is that we might, oh, I got this in the wrong order. We might understand this in terms of an idea from AI and from computer science, and that idea is what's called the explore-exploit trade-off. So the idea is, think about, it's a very, very general idea, applies to lots and lots of problems. There's two things you can do. You've got a problem to solve. There's lots of possibilities. Think of it as it's a big box full of solutions to your problem. Okay, so you've got this big box full of potential solutions, and you're at one point in the box. Well, one thing that you could do is you could just quickly get to a solution that's going to work pretty well. And that's the exploit solution, right? So you could just try and get something that will work and then implement it and make things happen out in the world. The other thing that you could do is you could try lots and lots of different things, including a lot of things that initially you think are not going to work. You could bounce around that box. You could kind of move from one part to another. You could try something that's way out, far away from where you currently are, and then quickly try something else that's even further away from where you are. So you could kind of bounce around in this noisy, random way through the solutions. And obviously, the first technique is going to be better at getting you something that works pretty well, pretty quickly, that you can actually implement so that you can go out and solve the problem. But the risk is that you're going to miss a better solution that's further away. So there might actually be a much better solution, but you're never going to find it because you're just making little small changes to what you already do. The second solution means you're going to waste a lot of time trying things that are crazy, that aren't actually going to work at all, but you might find something that's really a lot better. And the idea that people in computer science talk about is a contrast between a low temperature search, that's the first kind, where you're just trying to make small changes, this kind of exploit strategy, versus this explore strategy, where you're bouncing around as if you were a heated up molecule that was very bouncy. And again, who sounds bouncy, noisy, random, all over the place, versus who is sensible and focused and trying to just get through the day to get everybody to preschool on time, right? That kind of characterizes the children versus the adults. And that seems to describe these cases where the children are doing better than the adults. They're doing better than the adults in these kind of low probability when the answer isn't the obvious answer. Maybe I'll just, well, this is, so, you get that idea? And here's the way that it turns out the best way to solve it is this simulated annealing, where you start out with this very random, noisy, hot search, looking at lots and lots of different things, and moving very quickly from one possibility to another. And then gradually you cool off and end up just staying put at one solution. So if you were always at the high temperature, you wouldn't be able to do anything because you'd always be bouncing around trying something else. But if you're just stay at the low temperature, you're going to miss these better solutions that are further away. Everybody sort of got that? So if you just exploit, then you're not going to be able to find out all the ways the world works. If you just explore, you're not going to actually solve the problems that you need to solve. And the way that, that people in computer science and in other fields like optimality theory solve this is start out with a high temperature, start out exploring, and then gradually exploit as you get further into the problem. And the argument that I've made is that you could really think about childhood as being evolution's way of doing simulated annealing, of solving this explore-exploit trade-off. So the idea is you have this long period early on in life when all you have to do is explore because you're being taken care of. And then you, as a result of being able to do this very wide-ranging exploration when you're young, you can exploit when you're old. You can take all that information and put it to use to do all the things that organisms need to do when they grow up. Okay, I think since they're running low on time, maybe I'll just quickly go through this last piece. And it's interesting that many things that traditionally people have seen as being bugs of childhood, things that make children not as smart as grown-ups, things that are bugs from the exploit perspective are actually features from the explore perspective and vice versa. So being noisy, both literally and metaphorically, doing a lot of random stuff that doesn't really quite seem to make sense, having a lot of variability, being insatiably curious, right? Being impulsive and taking risks and playing instead of working. Those are all things that are characteristic about children, and they're things that often, not being very focused, having a much broader, more distractible kind of attention. Those are all things that are characteristic of children, and if you were thinking about just the exploit perspective, get things done as efficiently and quickly as possible, those are all real disadvantages. But if you're thinking about it from the explorer perspective, figuring out this weird thing about how these blickets work, that they're conjunctive or that they work on a two-dimensional rule or whatever else other weird thing there is in the environment, then all those things are actually advantages. Those are actually features. And those are all characteristics not only of human children, but of children in general, of young organisms in general. All right, so just the last point that I'll make, and then I'll stop, is, of course, all this depends on another feature of life history, which is what's called parental investment. So you can only do all that exploration if you have a whole bunch of people around who are your caregivers, who are committed to you, who are taking care of you while you're doing that. And if you look at humans, we have an exceptionally large amount of this kind of caregiving and investment. So not only do we have moms taking care of babies, but we also have dads, and we have alloparents and babysitters, and we have my personal favorite, postmenopausal grandmothers. You can see there's a grandmother lurking behind those 3 beautiful grandchildren. And what happens, I think I won't talk about that experiment. I'll just, oh, do we? Are we okay? All right. Okay, then I will talk about that experiment. So for humans, we have, for chimps, almost all of the caregiving is being done by the biological mother. But for humans, we have this, what I think of as this triple threat of lots and lots of people, fathers, what Sarah Hrdy calls alloparents, and then especially these postmenopausal grandmothers are all involved in caring for children. And it's that investment in care that is actually the thing that allows the children to do the exploration that they need to do. So it isn't just that, grandmothers and mothers and babysitters are around keeping the kids alive. It's because they're investing in the children that the children can do this amazing exploration, that the children can do this incredible learning that far outstrips that of any artificial intelligence. And let me give you one last experiment, not by me, alas, but by Nim Tottenham, who's actually also here in New York and Columbia, that I think really makes this point really beautifully. So remember I was talking about anxiety and the origins of anxiety? Well, the oldest result in all of psychology, going back to J.B. Watson, is this. Take a rat, you put it in a maze, it goes down one arm of the maze, nothing happens. It goes down the other arm, it gets a shock. Then you put the rat in the maze again, and what happens? It doesn't go down the arm that leads to the shock. That's like the most basic foundational kind of learning. Of course, that's what's going to happen. But of course, if you think about it, if that's what happens, how about if it turns out that next time there isn't a shock at the end of the maze? Maybe next time there's cheese, or maybe the shock only comes when in the daytime and not in the nighttime. The rat's never going to learn about what happens at the end of the maze if they just avoid ever going to the maze, like in that experiment with the Zafs. Well, it turns out that if you look at young rats, the equivalent of adolescent rats, which I think is about 14 days old, surprise, surprise, the teenagers actually want to go to the end where there's the shock. They'll prefer to go to the end where there's the shock than the end where nothing happens. But they only do it if the mom's around. So if the mom is present, then the juveniles will actually explore the place that has the negative outcome, which means that they'll get information about it, but not if the mom isn't there. If the mom's not there, then they won't explore. And what Nim discovered was that she did exactly the same experiment, but now with 3- and 4-year-old human children. And we do not shock 3- and 4-year-olds, but there was a really unpleasant noise, an unpleasant loud noise that went if they had literally, they had this tunnel kind of maze that they could go down either end of. And there was a really unpleasant noise at one end. And she discovered that the little children, the 3- and 4-year-olds, were exactly like the juvenile rats. If mom had, or dad, or a caregiver had been present in the first place, then they would explore. But if they weren't present, then they wouldn't explore. Then they just stayed away from the negative outcome. So it's actually having the caregiver there that seems to be the clue that says, it's safe. It's anthropomorphizing the rats, but it's kind of like the juvenile rat is saying, okay, mom's here, nothing bad is going to happen. Again, this will be familiar to those of you who are parents of 4-year-olds. And of course, for us as parents, the tragedy is we know that that's not true, but we still want to convey, we want to tell the kids, it's okay, as long as mom is here, everything's going to be all right. And it's because of that sense of as long as mom or grandmom or dad or the babysitter is here, everything is going to be all right. That's what lets you explore, and that's what lets you learn about how the world works. So I think there's really this kind of symbiosis between this exploration that the children are engaging in, this incredible ability to explore and learn, this motivation, not just ability, but motivation to do it, and then the very neglected, underpaid, under-resourced, overlooked work of taking care of those children. It's because people are taking care of those children that we can explore and learn as much as we do. And I'm just going to end. This is a little film of the Child Study Center at Berkeley, which is 100 years old. This was from the 1920s. And if you want a picture of sort of how this process works in real life, even 100 years ago, what's the sort of ideal context in which this kind of exploration could take place, I think you couldn't do better than looking at what life was like in the Child Study Center 100 years ago. I find this incredibly moving because, of course, these children are not with us anymore. But when they were 3 or 4 years old, they were exploring. There's people sort of sitting around in the background and making sure that they're safe. And as you'll see, they're doing all sorts of things that code wouldn't allow them to do in a preschool, nowadays. So let me stop there with these beautiful children and see if there are questions and comments and things to talk about.
And if you do have a question, please raise your hand. I'll bring you the microphone so everyone can hear it. I've got a question right up here.
Great.
Thank you. Have you, excuse me. Have you ever been curious or have you thought about whether the differences, I'm not going to call them benefits or deficits, but the differences between the cognitively immature, if you will, and the
Right.
cognitively mature could also occur, could also be observed between the cognitively impaired and the cognitively matured.
Yeah, so it's an interesting question about a specific example of this that we do know about that's interesting is, again, if you think about this life history, I didn't get a chance to talk about this for very long. One of the things that's distinctive about us is that we have this long childhood. But another thing that's distinctive is we have this long elderhood. So chimps, by the time chimps are, it's really striking for females, by the time chimps are 50, they're not fertile anymore and they're likely to die. We stick around for another 20 years after that, and we have even in forager cultures. And for women, for another 20 years after we're not fertile anymore. That's, again, very evolutionarily puzzling. And I've argued that that's another special niche. So it seems as if what happens is we kind of move from this early explorer to this kind of adult exploit, get things done, find your way in the pecking order, et cetera, to this postmenopausal grandmother phase, where now we're really not as concerned about our own resources anymore. What we're really all about is about taking care of the other people around us. And there's quite a bit of evidence for that. And there's some evidence that when in elderhood you get released from that need to exploit all the time to get the resources, you start getting some of the same cognitive advantages that you get in childhood. And then other advantages like being happier most of the time, which is an interesting one. So it's funny, I for a while I was saying, and I think this is true, that basically we're human up till puberty and after menopause. And in between, we're basically sort of glorified baboons. In between, mostly what we're doing is, going out and getting food and finding mates and finding our way in the dominance hierarchy. And all the stuff that's really human, like learning and cultural transmission and storytelling and causal inference, those are all the things that we do at either end. But then I decided after I'd spent some time with my adult children that maybe that was too harsh a way of putting it. I think the way we should put it is we're so lucky because when we're kids and when we're postmenopausal grandmothers, we get to do all this really human stuff. And then the poor adults in the middle only get to do it in the interstices when they get a little bit of extra time. It's not quite fair to say that they don't do it, but their lives are much tougher because they're trying to do it when they're trying to do all this other stuff like take care of the babies and the old people too. So I feel more sympathy for all you just regular adults in the audience.
Here's another question.
Thank you for a wonderful talk. I have a question regarding your experiment where you gave sticker rewards and took away double the amount of stickers. So there seems to be a loss aversion in the adults.
Yeah.
How do you think about it, and is there data showing whether this is due to more data that the adults had time to collect over lifetime of losses, or maybe something fundamentally different in brain development?
Right. Yeah, that's a very good question. And it looks as if one of the things that happened, so there's an interesting literature about risk aversion in general and changes in risk aversion over time. And it's a little complicated, but one interesting thing is that there's clearly less ambiguity aversion, as it's called, in children than in adults. And that's, I think, what's going on in this study. So children are risk averse. They don't want to lose the stickers. And if you just put them in a situation where it's straightforward about this is risky and this isn't, then they'll hang on to the stickers and they show loss aversion and risk aversion. But when it's like, do I know whether this is risky or not? Am I going to find out something? That's when you see the difference between the children and adults in a lot of different kinds of experiments. So it's about this trade-off between getting information versus getting loss or risk, rather than just about are you willing to take risks or not take risks. And by the way, there's a little work, this is a whole new set of ideas that we're working on. There's some interesting work that suggests that your early experience of nurturing or not nurturing, your early experience of life being good or life being bad, and particularly your early experience of whether people are taking care of you or not, really affects the developmental trajectory of this explore-exploit shift. So it affects things like, it looks as if what it does is it pushes you into exploit mode earlier. And we think that a lot of the negative effects of early adversity might be explained by saying that what it does is it pushes you into this state of exploiting too quickly without having a chance to explore. And you can see that in risk-taking as well.
This goes exactly to the question that I was going to ask, whether there was enough correlation of, say, low SES and high ACEs score children and this explore, exploit, reward system such that it is so impactful of a growth or fixed mindset that there's work being done to try and figure out how to undo that?
Yeah. Yeah, so that's a great question. And as I say, we have a paper that's just coming out raising this as a hypothesis. And there's some evidence that sort of suggests, there's a lot of evidence that suggests that early adversity accelerates development in general. So you get teeth earlier in a new study that came out. Kids who have more ACEs, these adverse childhood experiences, reach puberty faster. If you look at their brain development, it seems to go faster. And you might think, well, okay, faster development is a good thing, but it turns out that from this perspective, it's not a good thing. You really want to have that long period of exploration. And vice versa, if you put kids in enriched situations, so in a high-quality preschool, for example, that actually seems to stretch out the period of childhood. Now, the interesting thing is that when we looked at the Head Start kids and the kids in Peru, they were not showing any less exploration in these tasks than the kids in Berkeley preschools. And in fact, the kids in Peru were actually more exploratory than the Berkeley kids. But of course, when we looked more closely, we realized these are not children who are not being nurtured. I mean, the fact that you're in a Head Start program means that you have a parent who cares enough about you to want you to be in a Head Start program. And in Peru, these kids are really fascinating. They're what's sometimes called the emerging middle class. These are families that are immigrant families that are coming in from the forest and then coming into Lima. And they have enormous families and many, many people taking care of them. And they actually have more opportunities to explore than your typical Berkeley child will. There's more people to interact with. There's more of a physical environment to explore. So I think it depends a lot on what those dimensions are. But we very much think that things like those adverse childhood experiences where you really are facing, say, gun violence, to take a timely example, or poverty in the United States content, or I think even more importantly, isolation, which is what a lot of children are going through, and which is not at all what you're seeing in, say, the kids in Peru. Those things, I think, are exactly narrowing the scope of exploration. But we don't have very good data about that yet. That's the next project.
Hi, so I'm wondering, you were talking about how the language models aren't able to solve these type of tasks. I'm kind of wondering what your thoughts are on whether or not that's beneficial. There's been so much work on trying to actually constrain the outputs to be safer. I also kind of wanted to share, there's a really interesting paper from Felix Hill's group at DeepMind. He does a lot of developmental psychology inspired work, and they replicated Linda Smith from Indiana University, one of her experiments. It's the DAX and WASL experiment, And they actually got really interesting results. So it seems like using reinforcement learning and transformers. It seems like it's possible. Sorry, this is a little bit long-winded, but it seems like it's possible, but maybe not actually advantageous based on the kind of the goals of the language models. I'm curious what your thoughts are.
Yeah, a couple of general points about that. One of them is in terms of, everyone's been very excited, spending all their time talking to ChatGPT for the last month. And this will sound a little parochial, but I think we developmental psychologists have realized that you can't tell how someone thinks just by talking to them. So if you talk to a 3-year-old, you're really not going to get a good feeling either for their strengths or their weaknesses. You might think they can't understand some of these things that they do, and you might think they can understand a lot of things that it turns out that they really can't. And so we developmental psychologists, that's why we get paid the not very big bucks at all to think about control conditions and make sure that the kids are doing things and counterbalance and do all sorts of things to try and really get to what's going on beyond just what you'd get from having a conversation. And I think there's an important agenda now about, let's not just say, oh God, it looks so smart when we talk to it. Be psychologists, be cognitive scientists, but have these models as subjects, as it were, as participants. I'm not quite sure whether they count as a participant or not, but so that's one thing to say. The other thing to say is that my whole take about these large language models, and this is a whole other talk, is I think we're wrong to think about them as intelligent agents at all. I think what they really are is cultural technologies. So they're like print or writing or libraries. They're things that let us take lots and lots of information from lots and lots of other people and access it very quickly and efficiently. But they're not systems that are actually going out and learning about the world themselves. So they're very good at imitating. They're not very good at doing exactly the kind of innovation that kids seem to be so good at. But we, every time we give a talk now, someone in his laptop in the back is saying, oh no, I just got ChatGPT to do this thing that you said they couldn't do. So,
Alison, in one of the original experiments with the red and the blue block,
yeah.
You showed that kids can distinguish between 4 out of 6 compared to 4 out of 12. So they weren't just counting 4, but they were in some way understanding probability. Did someone also try 8 out of 12 and show that there was no difference between 4 out of 6 and 8 out of 12?
Oh, that's a good question. And I don't think that we did that, but it would be a really good experiment. And there are other, Molly would probably know about this, there are other experiments that show that children do seem to be understanding different probabilities as being parallel to one another, aside from just the number of items.
Thank you. Okay, coming with the mic for another question on this side.
Yeah.
When you talk about the different ways that children are processing things, do you see any implications of the cultures that they're growing up in? Mm-hmm. Like, is there any indication that the nurture and like the state of the communities that they're living in are affecting these processes, or does it seem to be mostly nature?
Yeah, that's a really good question, and we're just sort of trying to figure it out. I think the ACEs literature, that's the Adverse Childhood Experiences literature, and also the preschool literature, is a very good example of how certain kinds of environmental factors are making a big difference. And as I say, we haven't quite sorted out how much of this is exploring and exploiting, how much of it is sort of generally thriving. But there's no question that those kinds of, having really non-nurtured experiences early on versus having enriched experiences. And I must say, I'm kind of surprised by this, by how much impact it seems to have even late on in life. So the number of adverse childhood experiences you have predicts how likely you are to get cancer, or how likely you are to go to prison, or how likely you are to go to college. And I think part of the reason why I've been thinking about this explore-exploit idea is that, often when people think about things like the effects of high-quality preschool, it's as if they're thinking about school. So it's like, okay, well, you learn a bunch of skills, and then you're going to do better in school, and then you'll do better overall. But there's not very good evidence for that. In fact, what you find is that when you look at something like academic test scores, you don't see big differences at, say, 5th or 6th grade based on preschool. But if you look at whether you go to prison or whether you try. Here's an interesting example. If you look at SAT scores, you don't see a difference. But if you look at whether the kids try to take the SATs, you do see a difference. So I think what's happened is the kids in those enriched settings, it's not so much that they have skills that the other kids don't, but they have a sense of possibility. They think that there's more different things that could happen out there in the world. They have a greater range of things that they can explore. And that's what's making, I mean, that's at least the hypothesis about what's making these big differences in the long run. So I think that's an example where we really have quite good evidence that what's happening in the environment is making a difference. But it's making a difference in these kind of big, making a difference to some of these big things like how motivated you are, how much you explore, how much of a sense of wide possibility you have.
On the experiments on the conjunctive versus disjunctive and the children being able to spot more complex patterns than the adults. So is that, from the research, is that also a manifestation of the explore versus exploit, as in children take more time and hence figure out the more complicated pattern, whereas adults are grabbing for the more obvious one, or before, or is there something more to that that's still sort of unexplained or being explored in terms of why children are better at spotting those complex patterns?
Yeah, that's a very good question, and we don't know for sure. There's interesting work that suggests that there may be some very basic kinds of information processing abilities that are different. So here's a good example. Children seem to have a broader focus of attention and memory than adults do. So if you've ever played a game like Concentration, or there's an art version of this, one of those games where you have to find matches. Set is I'll bet people in this room have played Set with their kids. Set is a nice example. The kids are really good at it, and they're often better than grown-ups. And it's because they're picking up information that isn't just the information you're supposed to be attending to. They're picking up all sorts of unattended information. And again, that makes it them worse, and there's systematic studies that show this. If you have a specific goal, I'll briefly describe the study because it's quite a cool study. So you have a study where you have a whole series of cards. And the cards have red shapes on them. And then they also have blue shapes on top. And you tell people, okay, I just want you to look at the red shapes. Your job is going to be to tell me whether there are hearts in the red shapes or not. It turns out that, as you might imagine, grown-ups are better at that kind of task than children. But then at the end, if you have a surprise task where you say, okay, but how about the blue shapes? Were there hearts in the blue shapes, the ones that I didn't tell you to attend to? The kids are better than adults. So there seem to be some of these pretty basic information processing differences about, do you just pay attention to the things that are relevant to your goals, or are you paying attention to things that are broader? And something like that sort of internally seems to be going on too. Do you just pay attention to the hypotheses? Do you just pull up the hypotheses that are relevant to what you're trying to do now? Or do you search more widely, think of different kinds of things? And again, I think if you just hang out with kids. I've wanted to, I keep wanting to do this study. Evidently you guys are all too young to remember this, but there used to be a television show where they had an item called Kids Say the Darndest Things, where they just talked about, evidently there's a slightly more obscene version of this on the web about stuff that kids say. And if you just collect things that kids say, they do say a bunch of weird things. They call up ideas and strange, that just aren't the kinds of ideas that grown-ups would call up. So there's something about this very basic things like attention and memory and semantic retrieval, as cognitive scientists would say, that really do seem to be different. A lovely example of this, by the way, that I really like. I just see my grandchildren anymore. I don't see my children, but one of my postdocs, who's actually in Bear in the Berkeley AI group, said she was going for a walk with her 4-year-old on the Berkeley campus. And those of you who know the Berkeley campus, it has this famous campanile. It's a big clock tower. And the little boy looked at the clock tower and he said, "Mama, there's a clock way up there." And she said, "Uh-huh, that's right." And he said, "Why did they put the clock way up there?" And he said, "I guess they wanted to put it where the children couldn't break it." Which is a really great idea, right? Like, that's a good, like, why is there a clock way up there? That's as good an idea as any, but it's not an idea that a grown-up would retrieve.
Hi. Do you think children learn more in class or outside of class?
Okay, that's a good question. Part of the reason why I had that piece about the Berkeley Child Study Center is I think that's a really good example, sort of, when people say, what should children be doing? That's a beautiful example of the kind of context in which young children are learning. But remember, as much as I am really sympathetic with those wild, poetic, exploratory 3-year-olds, they have to grow up to be adults, right? I mean, you can't, if you just, you don't want your department chair to be an explorer person necessarily, right? Like you don't want yourself to be so busy thinking about all the things that you could do that you never actually do anything. So there's much to be said. I mean, not just much to be said. We wouldn't survive unless people made this transition to this exploit mode. And I think one thing that's happening in the school age period as opposed to the preschool period, remember that chart that we had, is that that's when that transition is happening. And if you look across, we've only been going to school formally for about 100 years, but if you look across much human history in many different cultures, around 6 or 7, children start apprenticing, basically. So they start learning how to be really competent at doing specific things. They learn to be exploiters between about 7 and adolescence. And that's kind of what I think something like school should be doing, as opposed to just the kind of free-form exploration that you're seeing with the preschoolers. Now, mostly what schools are doing is teaching you how to be extremely expert at going to school. And kids get to be really, really good at going to school by the time they are in our Berkeley, classes. They are just brilliant test takers and studiers. Now, what you'd want would be for them to be having skills that are, I don't know, maybe that's not such a bad set of skills to have, but you'd want them to have a broader range of skills. But I think that's what's happening in classes. That's what should be happening in classrooms. And, again, like learning skills like reading and writing and doing arithmetic, those are all really important skills that you need, and those are things that 7- and 8-year-olds are really good at learning.
I have a question that's maybe related. In terms of building intelligent machines, do you think that that transition is also important? So machines not only can explore and learn like children, but eventually grow up to behave like adults, or more like be able to switch between maybe a child's mind and an adult's mind?
That's a great question. And one of the things that I've argued is that, and it's interesting because if you actually, this explore, exploit, high temperature, low temperature annealing idea comes from computer science. And when you talk to people who are actually doing things like using neural networks, designing these systems, they'll tell you, oh, it doesn't work at all unless you have an annealing schedule. So you have to have a way of going back and forth from exploring and exploiting. But it turns out that, as is often the case with AI, they just kind of make it up as they go along. So basically what they'll say is, yeah, well, we have a temperature switch, and then we just fiddle with it until it works. So there's a really interesting question about what's the principle. The one principle that everyone seems to have is start out exploring and then move to exploiting. But a lot of times if you do more than one round of this, that's actually the best thing. So explore for a while, then exploit, then go back to exploring, then exploit, then go back to exploring. That seems to be a good way of making that kind of balance. And I didn't go into this in the talk, but I think there's reason to believe, for instance, that adolescence is a period when you're back into explore mode, but you're back to explore mode for a particular domain, which is social life. So, you may not be exploring the Blicket detector, but we've done other experiments that show when it comes to social learning, you see much more flexibility in the adolescents than you do either in the school-age kids or the adults. So that may be like another round of high temperature search, which again kind of fits your general impression that teenagers are as nutty as 3- and 4-year-olds a lot of the time. So I think that's, and of course for adults, for human adults, one of the things that we do is work out ways that we can go back and forth between exploring and exploiting. And I think there's a lot of human practices like retreats, like religious practices, like meditation in various forms, which are part of these religious practices, that are really ways to kick us out of our local minima, give us a, and it's interesting that in order to do that, what we have to do is not be working, not be planning, not be trying to get things done. And just when we just sort of can sit quietly, breathing and not thinking, as it were, that seems to often have the effect of letting us figure out new things, find out new things.
To your earlier point about the 6- and 7-year-old apprentice.
Yeah.
What are your thoughts, pros and cons, with regard to other countries that track children in their early educational development, and they determine maybe by the 2nd grade that you're going to go into law, or you're going to study medicine, or you're going to study math?
Well, I think if you look at the context in which this exploration is really useful, and this is, I think, an interesting point, it's when the environment is sort of variable and unpredictable. And that actually seems to be the ecology that led to human evolution. So if you know that you're going to be in an environment in which most people are going to be farmers, then it makes sense to get kids to be farmers. But if you're in an environment that is much like the environment that most of us are in, that's much less predictable, much more variable, then keeping this window of exploration open for longer, even through, as I was saying, even through adulthood, is a sensible way of trying to deal with a less predictable environment. But again, I really want to emphasize this. In America, we hate trade-offs. In California, we really hate trade-offs. Even in New York, I think people are not crazy. New Yorkers have a more tragic sense of the world, so maybe they can think about trade-offs more. But we don't like the idea that we can't just have everything and have everything at once at its highest level. And there's the explore-exploit trade-off is a real trade-off. So you could have the advantage of being able to deal with more different environments if you're exploring, but that also means you're not going to be as competent in any specific environment. And you have to figure out divisions of labor, either these kind of developmental ones about different developmental stages, or maybe different people. So you have scientists who are allowed to go out and just wildly, or artists who can wildly explore, and then you have CEOs who actually go out in the world and make things happen. We have different ways of trying to resolve those trade-offs. But as much as I obviously am sympathetic to those crazy 3-year-old explorers, it's a trade-off. They can only do that because they've got a bunch of moms who are adults, moms both female and male and related and unrelated, who are willing to do the hard work about, okay, what's going to happen tomorrow? What's the schedule like? How do we get you to the preschool? What's happening with that, pediatrician's appointment? That you need to have that in order to be able to have the exploration.
Hello. So childhood, as we know it today in terms of like caregiver nurturing, is a fairly kind of new concept. And I was just wondering how you think that has kind of impacted children's learning and development.
Well, I guess it depends. I mean, it's interesting because if you're sort of the self-conscious idea about childhood is relatively new. But if you look in forager cultures and you look historically, I mean, especially if you're talking about early childhood, you had to have caregiving because otherwise you'd die, right? I mean, and in the old days when 1 out of 5 kids was dying, it was even more important that you have people take care of those children. And when you look in other kinds of cultures, it's interesting because it's not, I mean, when I give these kinds of talks to this kind of audience or in the Bay Area, people say, oh, good, okay, so this is what should I do to make sure my children are exploring, right? So what's the formula that I have about, how can I be a gardener instead of a carpenter? Like, could you write this down for me, please? Or can I put it in a robot so it could do it instead? It's that's very much the attitude. And if you look in other cultures, people would think it was really weird if you said to them, well, are you doing that because you think, are you letting your child, pick up the knife and make the tortillas because you think that that's going to let them explore? That would just be sort of, no, it's because that's what children, that's what children do. That's the sense in which I think the caregiving and the nurturance has always been there. It's always been part of it's always been part of what we do, and it's very ancient evolutionarily. Look at mammals, that's kind of the definition of mammals. But it's a sort of self-conscious sense about, oh, here's what I have to do to nurture my child that's much more recent, and probably something of a mixed blessing, I think.
Hi. Do you think that I know you said that for preschoolers that having parents that put them in an enriching environment gives them better, like they're better at things when they get older.
Mm-hmm.
But do you think that parents taking a more active step when the kid is more like 2 or 3 years old has a big effect? Because I know like when it comes to language acquisition, parents trying to like teach the kid to talk or like respond the word back to them has little to no effect. So
Right.
like the same
So
statistics.
there's a really important distinction. This is something that I'm working on now between caregiving or caring and teaching. One thing that we do is we teach, and it's important that we teach. But caring for someone is really different from teaching them. And one way that you could, I've been working on some of these ideas recently. Here's a way of thinking about it. What do we do? And caring, it's funny because caregiving is something that is so ubiquitous and so important, and yet we don't think about it very much, and politicians and economists and philosophers haven't thought about it very much. When you're caring for someone, what you're doing is taking that person's goals, and so here's the situation. You have more capacity than that other person does that you're caring for. That's what makes it caring. You can do all sorts of things that the other person can't. But you take all those capacities, and instead of putting them to use to accomplish your own goals, you put them to use to help the other person to accomplish their goals. That's a really strange, interesting kind of human interaction. And it's very different from saying, I want my child to go to Harvard, so I'm going to do a bunch of things, or NYU or Berkeley. And I'm going to do a bunch of things, and as a result of that, I am going to accomplish my goal of having my child be happy, successful, smart, whatever it is. And those are so different from one another, but I think, especially in our culture, we tend to conflate them. So we act as if this act of caregiving is really about shape. My book is called The Gardener and the Carpenter, because the idea is it's the difference between thinking, okay, I'm going to shape this child to come out a particular way, and if I just do the right things, I'm going to be able to do that. And empirically, that doesn't look like there's much chance of your being able to do it. And even if you could, you'd be kind of defeating the whole purpose of childhood, versus saying, I'm giving my child this background of nurture and some space and a certain kind of safety that will allow them to explore, which I think is what the caregiving story is. And there is evidence that that kind of caregiving, whether you get it or not, does make a difference to how you develop. I'm sorry, that was a bit long-winded. So, the short version is it's one of these kind of Buddhist paradoxes where, insofar as you're trying to make your child come out a particular way, you're probably not going to succeed. And insofar as you're not trying, you probably are going to succeed. Kind of a Zen in the art of parenting idea.
You know so much about early childhood development. Was there anything that surprised you with your own grandchildren?
Oh, everything surprises me. Everything surprises me about my own grandchildren. I'm a scientist, so I always think that it makes sense and fits my theories after the fact, but one thing that, again, fits my theories after the fact, but I was a little surprised by was how much, as a grandmother, your interactions with the children are different from the way that they were with when you were a mother. And how much the children look for different things from grandmothers. And my favorite recent example of this is so one of the things about grandmothers is that I think they're really important for cultural transmission. They're really, and there's evidence for this. One of the things that grandparents and elders do is, instead of sort of this job of keeping the kids alive and functioning and getting to preschool and so forth, one of the things they do is pass on the big ideas about the culture, the big stories, the big traditions, the big moral principles, and the recipes and the songs. And one of the things that I discovered with Thalo, the beautiful baby that was there, is I find myself singing 1950s Hollywood Broadway songs to him, so like the whole Broadway songbook. And that's completely how he identifies with me. So when he goes on FaceTime, because he's in Montreal, he says, Grandma, lullaby of Broadway, lullaby of Broadway. I've been so happy to be in New York. Rumble of the subway train, rattle of the taxis, Angelo and Maxie's. And so I've realized that I am completely identified with 1950s Broadway show tunes as far as my grandson is concerned, which I am surprised by. I'm surprised that he has managed to memorize all of followed by a Broadway. But I think it does fit this broader picture about grandparents. I don't think I ever quite had that. I never had a relationship with my children that was so grounded in being able to do old show tunes, sing old show tunes.
Thank you so much for such an informative and inspiring talk. And I was just wondering, especially for the explore versus exploit, and you said that adults tend to use exploitation more than exploration. Is it possible that, and you also mentioned about like the strong priors that adults have. Is it possible that like how adults benefit from exploration in their own childhood actually act as like a prior in like how they decide they're going to explore and exploit?
Yeah.
For example, like if they like benefit a lot from their previous explorations and they tend to explore rather than exploit.
Well, I think one way of thinking about it, this gets back to this point about, do you think that the environment is going to be rich and variable, or do you think the environment is going to be harsh and predictable? That's one way of thinking about it. And you could think of that as being a prior, right? So if your prior assumption is things change a lot, but mostly they're good, mostly I'm going to be able to get resources, and they're not going to change in a way that I don't understand. I'm going to be able to understand it. That's a really different feeling, attitude about the world and way of dealing with the world. That's kind of explore prior, as opposed to things are harsh and tough, time horizons are short. That's a really important difference. And it's likely to be the same bad things happening over and over again, which I don't have much control of. So I think you could definitely cash this out as if it was a kind of explore prior about what the environment's going to be like, rich, variable, somewhat but not totally predictable, versus a kind of exploit prior about time horizons are short, life is rough, and it's not very predictable.
Okay, any last questions? Well, I just want to express my thanks to all of you for coming. Yes, I hope you'll come back to more MoMath programs. And incredible talk and wonderful questions from the audience that really, we had a wonderful discussion even after the talk. So I'd like everyone to join me in please giving a nice round of applause. And we'll end with that. If you have any quick questions that you want to come up and ask, please feel free to do that. Otherwise, get home safe and hope to see all of you again soon. Thank you for coming.